Thank you, Katharina. Thank you, everybody, for being here. Thank you for the organizers for putting together this nice conference. I was lucky enough to be here for the last one that was mentioned earlier today. I went and looked it up. It was October 2023. It seems much more recent than that. Yeah, but it's good. It was good back then, and so it's great to be back. So what I'll tell you a little bit about today is a potential application for what we could do with a quantum computer in the near term, and sort of our work in that space. I've had, I have the good fortune that I'm following Matt and all the talks this morning, so you all will have already had a great introduction to some of the things I'm going to say. I should thank the people that did the work. Primarily, this work was done by Norman Hogan, together with Efkan Köksü, my former student, who is now at Central Florida, and a bunch of excellent collaborators, including Dan, who's here in the audience, who has never seen this talk, so this will be fun. All right. I don't have to show you this, yes? Quantum advantage. So one way to think about the state of quantum computers is sort of on this sliding scale. So on the very left, you have what I would call a bespoke quantum simulator. We've had these for a long time, in various scales, right? People that in their lab build a thing. In this case, what I have is a stylized representation of like an optical lattice, and use it to simulate some quantum system that you care about, right? The idea is you build a quantum system that represents the quantum system that you actually want to study, and you use that to study its dynamics. On the right, you've got our eventual, pie in the sky target, right? Like these are the sorts of like industrial scale applications that I might want to do. I might want to ask about vehicle routing problems, cell tower placement, all these sorts of things, right? That's eventually where we'd like to get. I would argue mostly we are on the left side of things these days. A bit better, we can start to look at some of the things that physicists care about, these sort of Kagome lattices and these kinds of things. Okay. Okay, so this is where we are. How do we think about quantum advantage in this context, or what is my definition for this? My definition. When can I use a quantum computer to answer a question relevant to a condensed matter physicist? So when I was a postdoc, I worked with Tom Devereaux at Stanford, and we had a long-standing collaboration with a physicist named Doug Scalapino, which may be a name that some of you know. And one of the questions that Tom would ask me is Doug going to care about this? Right, so the question really is this a thing that somebody outside of our community, can we do something that somebody outside of quantum computing will go, oh, hey, that's cool. I didn't know they could do that. Right? So they could actually sort of sit up and be like, well, maybe this is a tool I would like to look into. Maybe this is something I want to invest my time in. And this is for the people that are not already occupying this space, right? What kind of problem might I pose for this, right? What sort of things could I consider doing? Well, to get to this type of quantum advantage, you need something that's relevant or interesting to the people that are not us. You want to be able to talk to them, right? So as much as, we like hearing about lattice surgery, they're not going to understand it because they don't have the background to do it. So you need something that they can understand. You probably, for near term, want to run this on some small number of qubits. So you want the thing to run on 100-ish qubits and that to be relevant. And finally, you can't require long coherence times yet. Now, if you think about fault tolerance, right, and starting to move towards that, we can extend some of these things. So I want some kind of problem that is relevant and interesting at all of its scales. So I can run something that's small, and that'll be something that's interesting. And as it gets larger, it gets better. This is sort of the same statement. Something that can make use of limited amounts of longer coherence times, maybe some of the qubits, right? Different ways of thinking about that. And also something where I can incorporate some type of fault-tolerant element, right? So say somebody comes up with a really, really good fault-tolerant time evolution algorithm. That would be great to be able to insert that, right? Or these types of things. So my proposal to you today is that one of the things that fits all of these is something called Dynamical Mean Field Theory. All right, cool. So now show of hands. Who has heard of this before? Excellent. Who thinks they know what it means? All right, great. Far fewer, perfect, okay. So the way this works is as follows, right? is you are interested in solving some kind of lattice model for your material, Hubbard model or generalizations of that. What you do is you build yourself an impurity model. What that is some interacting impurity surrounded by a bath of non-interacting things. You then discretize it, you solve some things, right? For example, in this case, a Green's function. And what you do is you essentially adjust all of these parameters until the quantity that you care about, in this case, electronic properties. It could be Green's function, it could be self-energy, it could be 1 RDMs and 2 RDMs. One of these properties matches the one from the lattice. So you require a self-consistency by solving an auxiliary problem that you then continue to update. You update the problem until you are in agreement with what you would get from the lattice model from a similar calculation. Okay. That's a lot. Yes, question?
What does the Green's function have to do with the description of the bath?
It doesn't. The Green's function is the one so you have, okay, great. So a longer answer. The reason we call it dynamical mean field theory is that mean field theory is valid in the limit of infinite coordination number, so all that matters really is like your local properties. So what you want is you want the Green's function for the impurity. That's the one you care about. The bath is there to provide you like a place for the electrons to interact with so that you have sufficient freedom that you can represent the real problem. Yeah, you can think of him like variational parameters in some kind of sense. This can be extended, I can do clusters, all these sorts of things. Why is this good? Because one reason is I have a smaller problem that via this embedding procedure I can use to answer a larger problem, rather than just doing exact diagonalization or quantum computing on the whole large thing. Yes?
Bath site have to pay, like usually? Is there?
How many bath sites do you need? More is better. So we don't have an answer. There are varieties of ways of doing this. I can do this with exact diagonalization or quantum Monte Carlo, a variety of things. And essentially the answer is almost always more is better. The more I can add, the better my approximation is. What I would love is for like 100 bath sites. That would be amazing. Yes, Athena.
Does each individual orbital require its own set of bath sites, or can you reuse bath sites for different orbitals?
You have a choice. You get to pick the topology you want. In this case, what I've drawn is I've drawn each individual impurity orbital to have its own baths. You do not have to do that. Yeah?
What does dynamical mean in this context?
Fantastic. Dynamical mean field theory means, so traditional mean field theory in like the Curie-Weiss sense, right, is I have some spin that interacts with all of the spins around it, right, and that provides some local energy. In this case, what we do is we use an equivalent called the local self-energy. It's like the effect of all of the things around it. It is energy dependent, so it depends on the frequency or the energy of the electron you are working with. So it is like the electrons sit in a dynamical field, a field that varies as a function of time or frequency. This is the dynamical bit. Do not be fooled by the name mean field theory. It is not solvable. I've gotten this critique on proposals where they're like, why are you doing mean field theory? We can solve mean field theory. No, okay. Yes, Matt.
You take a big problem and you make it smaller.
What's that?
You take a big problem and you make it smaller.
Yes.
And then it's easier.
The solving for the Green's function is easier. Yes.
Well, in some limit, you make the problem so small that it's solvable on a classical computer.
Yes.
That's what we do today.
Yes.
Dynamical mean field theory.
Correct.
So this seems to have the same-ish problem that we have in the chemistry things we said, which is at some point it's small enough that classical algorithms can attack it.
Yes.
And so maybe you're going to tell me something special, that this is sort of different than just ground state energy estimation. But there, 76 orbital FOMOCO is solved, according to Garnett-Chan.
Yes.
You want to do it with less than 100 qubits. So your problem has to have structure that is extra special and extra hard and extra quantum amenable, or I can just do it with DMRG or TRIM-CI.
Yeah. This is really great. Some of those things I'm going to talk about. For the other point, the reason you want to do this over just solving just like a larger lattice problem is that by using, say you top out at 30 qubits or 50 qubits or 100 qubits, yes? You will gain something in addition to, or more than having just solved a 100 spin orbital Hubbard model. This is why you do this.
Right, but you use the word qubits, which I think is not necessary.
It's not.
Because the same argument can be made if you top out at 30 sites on a classical computer, 50 sites, or 100 sites, you gain something that you wouldn't have otherwise.
Yes. Yeah, but okay, so fine. But if you want to do like the classical exact diagonalization approaches for this peter out at 10, 15 sites.
Right, but you don't use exact diagonalization, you use DMRG or...
People do.
Right.
People do. It's an option. DMRG is an option. Quantum Monte Carlo is an option. Exact diagonalization are an option. They all have their own limitations. Yeah. Yes.
Do you retain the periodic structure in the impurity model, or is it not like just the?
You do not retain okay. At the DMFT level, you do not. You can do other versions called dynamical cluster approximation or cluster DMFT where you do. So it depends. Yeah.
One last maybe naive question. For the arrow on the lower right, you have it pointed back to the lattice model itself. Should it instead be pointing back to the Bath model?
No, you pass this through here. You pass this through some agreement with the lattice model as well. You never fully diagonalize the lattice model, so that's not what you do. But there is a way in which you incorporate it. Yeah. I didn't want to kill everybody with equations, so I can draw this out and talk more about it. Okay. What does this do for you? Well, one of the places this is used is not just in DMFT, but you use it in something called DFT plus DMFT, where you bolt it on top of sort of classical quantum chemistry methods to try and incorporate some of the interactions. What that does for you is it turns these sort of spaghetti band structure plots into something much more exciting, where you can learn something about the line width. You can look at complicated. And by complicated, I mean harder to handle elements. Plutonium is difficult because it's got F electrons. They'll tend to really want to localize. They need strong correlations in order for you to get them right. And these are things that people look at with DFT plus DMFT. So it's a thing that people can use beyond just for lattice models. Well, yeah. OK, good. Certainly this has been done. Oh, sorry. So now the idea is we'll take this and we'll offload this bit, the impurity model, to the quantum computer, right? So I would want to calculate a Green's function. Typically, I would do that with a circuit that looks like this. It's got a couple of the standard steps. I have to prepare a ground state. I have to apply some operators, time evolve, and then measure in this Hadamard test way this correlation function. Relatively standard, comes with all the problems that we know about. Okay. We're not the first ones to do this. There's quite a few papers on this. This is now out of date because there was another one last week. The red ones are the ones that I've shown here on the left. And so some work that we've done, we're able to get sort of very limited sites. So this is for like two-site DMFT, like you can help get converged phase diagrams and that sort of stuff. So it's doable, and lots of other people have worked on it. What I want to tell you about today is how we're going to address these bits that I just pointed out. Because you have to prepare a state. This is hard. Why is it hard? Well, it's an interacting state. Yes, okay, it's for an impurity model, but it's nevertheless interacting, so you have to prepare a ground state for that. That's not easy. Variational approaches, we know what all the issues are, baryon plateaus, and that sort of stuff. Time evolution is also complicated. The standard triad decomposition gets you very deep circuits. Alternative approaches are not quite viable yet. They may be nearby. And this is one of the places where this is a nice problem for this sort of early fault-tolerant stuff, right? Because you could take some of these widgets out and replace them by fault-tolerant widgets. Because you've got a couple different pieces. And so depending on what the community comes up with, right, there are places that you can plug this in potentially. And finally, no matter what you do, your results are going to be noisy anyway. You're going to have some noise to deal with. And so what's nice about looking at Green's functions, correlation functions in particular, is that there are techniques that you can use on the classical end that help to fix some of that. So I'll give you the punchline first, so you can zone out. We're going to use some subspace expansions for state preparation, some Lie algebraic methods for time evolution, and then some classical post-processing techniques. What these look like is I'm going to build, very similar to what Matt just did, I'm going to build a subspace, except I'm going to pick free fermionic states to do that. It's Gaussian states, and there'll be a good reason for that. We're going to use some of our Lie algebraic methods to do a partial compression of the time evolution. You cannot do a full one because it's an interacting model, and so therefore, okay, if I could compress this, then quantum mechanics would be easy, and it's not. So this is not possible. So these are the things I'm going to tell you. Okay. Cool.
Like, sorry if I can interrupt you. Can you say anything about the number of circuit repetitions that you need in order to get the precision you want for computing the Green's function?
You mean like the number of shots?
Yeah. I mean, in the context of like DMFT, using it for
Yeah.
DMFT.
The problem at this point on today's hardware is not the number of shots, but it's all the other error that comes with it. So I cannot answer it because I don't know, right? Like gate error and decoherence and the other things cause me bigger trouble than any shot number does. Okay. That being said, what I will say is like if I get to the classical post-processing bits, right, it turns out that you're a lot more tolerant of noise in calculating these sorts of things than you are in calculating like a ground state energy. Because you're looking at a correlation function, which is a whole series of numbers and not just one number. So you have a bit more freedom to work with. Okay. Yes.
So one quick question. So when you say circuit compression, I was just always wondering, like, does this mean reducing the complexity or reducing the perfection of the algorithm?
What I mean is reducing the overall number of gates to something that scales with a smaller power of your number of time steps. Okay.
Yeah, so, you will try to apply this compression to the characterization technique?
Yes. Yeah. There'll be details for each of these, but I figured, okay. All right, cool. So let's do the first one. So as it turns out, and this is kind of cool, and this is one of the reasons I think this makes for a really good model to play with, is that impurity models are special. You can quantify this, but the way that they are special is that they are tunable from something that's free fermionic to something that's fully interacting. How do I quantify this? What I can count is I can count how many Gaussian, how many free fermionic states I need to represent the ground state of this impurity model as a function of how many impurity sites I have and that sort of stuff. There was some lovely work by Sergei Bravi on this. There was some lovely work by Bella Bauer on this. But suffice to say, for impurity models, you need a number of Gaussian states. If you don't know what the word Gaussian means in this context, you should think easy. You need a polynomial number of these in order to represent the ground state to some approximation. Because they're easy to prepare on a quantum computer. More importantly, once I find a basis set of these, what we found is that you can span the whole DMFT phase diagram with the same basis. So this basis set is not just for one point, it's usable sort of across the spectrum. And you can tune this, right? You can make your impurity more complicated, where you need more and more and more and more of these. So you have tunable complexity for your problem. This is helpful as you're trying to find a problem that is relevant to a quantum computer that you might have access to.
Lex,
Yeah.
Going back. So on this bullet, polynomial size calculations.
Yes.
Is this like empirically observed, or is this like there's some complexity here?
Both exist. This one I think has the complexity theory one of these two.
Okay, so is it like it's an existence thing? Like there exists
Yeah, but no, the power I think is known even. But it depends a bit on the details of number of bassites and number of impurity orbitals. So the expression is not helpful to just have on the screen, but it exists.
Or I guess I was more saying like, is it, I'm trying to find the catch. So is it the case that obtaining those fermionic states that are a good approximation is itself a hard problem?
No. All of this, is relatively easy as long as you can handle however many chi's you have. As you tune towards the right, this number goes up. Eventually, you will need something that looks like an exponential number. But early on, you don't. Yeah. We've got so many. Go ahead.
Yeah, I was just going to add, I think that the probability result is it's polynomial in the number of bath sites.
Yes.
It's still exponential in the number of impurity
Yes.
sites. So if you have a more complicated impurity, that still grows exponentially.
Which you have to, because eventually you have to get to this point. Yes, when your number of impurities is your full lattice site, it has to be exponential. Yeah.
Oh yeah, so I think that's all. Also, my question. So if this linear combinations is just a polynomial size, this means this problem is classically easy.
So again, he's right. He did a much better job. It is polynomial in number of bath sites, but not number of impurity sites. So it depends which problem you're doing. Art.
Yeah. So how do you define this impurity model Hamiltonians? Like not in the diagrammatic sense, but can you write them in the second quantization?
Yes. Yeah. So these bath sites are just like C dagger Cs. So these are hoppings between the two. That's what the lines mean. The single lines mean hoppings. I've got Coulomb interaction on each impurity site. And if you have a multi-orbital impurity, then you have the 4 different types of Coulomb interactions. So Coulomb, interorbital Coulomb, Hunts, and pair hopping.
So then your solution and number of chi's, or the chi number, is determined by the structure of this Hamiltonians, right?
Yes.
You could always know what chi is.
No. No, you can't. I mean, no. How many so as you make this problem harder, your chi will need to be larger. I don't think you a priori know how many.
Okay, what's the statement then that there should be some, because a full CI solution could be written in this form, right?
Yes.
So it's later determinants, but
Okay.
chi is exponentially large.
Maybe let me take a couple of slides and then we'll show you some data, and then you'll see what I mean. It's okay? Okay. Okay. Brief detour. I'm going to take one more ingredient to this. This basis that I find actually does a pretty good job for a lot of different parameters that I might put here, for different U values, different hopping parameters. Why is this useful, or why should this be so? Well, as it turns out, the ground state manifold of an impurity model, but really anything, is spanned by just a few states. You don't need all that many. There was a lovely paper on this a little while ago called Eigenvector Continuation with Subspace Learning, where what they did is they looked at the 3D Bose-Hubbard model. Here is what its spectrum looks like as a function of U over T, right? These stars are the exact energies. Perturbation theory should be valid from here in small regions, yes, near U equals 0. And it does okay up to this sort of like critical-ish point where it completely fails. First order, second order, third order, it just doesn't work very well. What you can do instead is you can build yourself a subspace, say by taking this point, and that point, just a 3-dimensional subspace. In the same sense that Matt just talked about, compute the overlaps, compute the Hamiltonians, solve the generalized eigenvalue problems, and the line you get is this black one. All right, so with very comparatively little effort, you can get the spectrum across the whole phase diagram. You can do this also if you pick them nearby. Of course, your matrix is much worse because these vectors are much more like each other than these were, right? So you run into conditioning problems and all that sort of stuff, right? But classically, that works pretty well. This turns out to be useful for quantum computing also. Here, this is not quantum, but we applied it to molecules. I don't know anything about molecules, but luckily Carlos did. Here, what we did is we said, well, okay, let's apply this to the situation where your state preparation is not particularly good. So you do a VQE, but you don't do a good job. It costs too much. You do adiabatic state preparation, but you also don't do a good job because adiabatic state preparation requires that you go really, really slowly. Right? So that moves you off of the ground state manifold, which is not great. But then if you take these vectors that you found along the way, use it to build your subspace, solve your generalized eigenvalue problem, these are the values you get. Right? So even though your ASP didn't do a very good job at all, right, simply by recognizing that it does have some aspect of your ground state in it, and you have enough freedom in your basis that you can perform Gram-Schmidt, which is what you need to do, right? You can fish out what the ground state is and get a reasonable ground state energy. Yes?
I have a question on the previous slide.
Please. Yeah.
So you took the superposition of only in the right panel, the 4 points are really nearby each other, and then still recover the entire black curve.
Yes.
Oh, that's very surprising.
So the overlap matrix you get from this is horribly ill-conditioned, right? Because these vectors are all basically the same.
So I would expect that the subspace is...
But these are good enough. The condition matrix is not so bad that you could not invert this. So bad, but not that bad. Okay, this is classical calculation, yes? So I have 15 digits of accuracy, which is a different problem, right? But yes.
Still captures.
Yeah.
Yeah, so then I guess this cannot tolerate a lot of noise.
If I pick them here, no. No way. If I pick them here,
yeah, sure.
Possibly. Yes. Yeah. Okay. Okay. How do we apply this to DMFT? Well, we'd like to represent my impurity wave function as a sum of some Gaussian states. Gaussian means easy, means non-interacting. So what we do is we pick states from, I sample over all the possible Hamiltonian parameters I can have for the non-interacting impurity. So I said U to 0. I just have some non-interacting impurity model. This is easy to solve. Yes, it's a polynomially sized diagonalization problem. These form my basis of fermionic Gaussian states. Using that basis, I now express the interacting Hamiltonian and diagonalize. And so using this basis, which turns out to work across the entire DMFT phase diagram, you get the correct energy and ground state for the interacting Hamiltonian. Okay. Now your question, how many? Okay, so what I have here is the fraction of the full Hilbert space that I need, that I would need to represent this problem. So this is for 1 impurity site, 2 impurity sites, 3.
You're saying like per orbital, right? Like so pure. Oh, sorry. Go ahead. Sorry, go ahead. I was confusing bath and orbital.
There are 2. The horizontal axis is as I increase my number of bath sites. Then you're fine. The different lines are as I increase the size of the impurity. Right. So 100% of the Hilbert space is up here. Right. We need a much smaller fraction of the Hilbert space. The fraction increases as I increase my. Are these labeled backwards? They might be. Anyway. The fraction you need is much smaller of the full particle selected Hilbert space. So it's an efficient representation. Eventually it has to fail, because eventually I reach to the point where I have a full interacting lattice. But for for up to 3, 4, 5 sites impurity sites that we've tried, this works pretty well. What do we care about? We care about the impurity Green's function. And so this is, as a function of number of path orbitals, and it lines up nicely. This is all done on a classical computer, and it's all really easy, because these are all Gaussian states. They're fully characterized by just some matrices that are polynomially sized. So this is all effectively free. You don't have to do any hard work for this. Yes, it's an interacting problem because the Hamiltonian is interacting, but we evaluate the elements of the Hamiltonian in a non-interacting basis, and that makes it easy. And then you can do DMFT with that. Great, it works. Okay. Okay, questions for this before I move on? Because the next bit will go a little bit quicker. All right, here we go. Okay. So I don't have time to talk about this in detail, but there are some clever tricks that you can play with time evolution. In particular, if you have Hamiltonians of this form, for example, an XY model, where maybe I want to do trotterized time evolution that looks like e to the xx, e to the yy, the sort of standard things, these things are compressible. I can take any number of these that I want and compress them into something that is this depth. Why is this? Because the XY model is a free fermionic model, so I have to be able to do that. Works for a transverse field Ising model, works for XY model, and that's about it. Right? The moment I add into any interactions, it doesn't work. Okay. So that, of course, leads to problems because now what I'm going to tell you about is an interacting impurity model. Right? I have to skip one or two things in the interest of time. Good. So what are we going to do? So let's consider, for example, a single trotter step. Right? I have my bath sites. Remember, those are non-interacting. The hopping to the impurity sites are non-interacting. The only interactions I get are on the impurity themselves. So if I break that into the same pictures I just had, previously I drew you a square. You can do a triangle as well. You end up with these little match gate triangles with a single ZZ in the middle. Bless you. Now, if this didn't exist, I can just compress this all at once and I would be done. But it functions as an effective block that prevents me from doing that. But what I can do is I can take these three up here and compress them over there, and move them in. And I can take these three up here and compress them over there because they don't touch the Z. Yes? Effectively, you can think of it like e to the I xx plus yy with some combination. Okay? Good. Match case are the things that are compressible. So, they're classical symmetry also. So that means I can write the same circuit with fewer gates, right? And then sort of shove them together and make a single compressed trotter step. And of course, I can stack this, right? I can do this with 3 trotter steps. I can eat all of those. I can eat all of those. And in the end, have something that looks much smaller. One of the cool things, yes?
Yeah, so maybe I misunderstand it. So I think here you basically use some light cone argument.
No. No. These get absorbed into here by changing the angles of these gates. So it is not light cone where I am taking them away. I am saying that you can take this and express them as a single one of these. And it's the exact same quantum operation, and you can efficiently find what it is. So it's not I'm taking them out because of light cones. I'm just absorbing those into the gates on the left.
Okay. And the axial bus becomes bigger, and the bigger the constant factor you are saving also becomes bigger.
Yes. Yes. This is a great observation. Yeah.
Does it still work if I have transverse field terms like single side, x rotation, say?
Transverse field. Okay. So if my Hamiltonian is xx plus z, yes. If it's xx plus an x, does not. And that's because the first one is integrable and the second one is not. So it has to be. It works for bits of the model that are integrable. Yeah. Good question. Yes.
Just double check, because after the compression, it seems like the circuit depth is not reduced because you still have 3m after each ZZ.
Good. So the number of so the depth, no, but the number of gates, yes. Well, hold on, wait a second. No, sorry. Yeah, so let's be clear. I ate those. Those are gone. I ate those. Those are gone. Yes, so the maximal number here was 15, and now I'm down to 7. 6. Yeah. Yes?
So just to clarify on that point, so is all of the infidelity that did exist in those gates now being subsumed by the gates that you folded them into, or are you saying no, they're actually now they're virtual and free?
They're virtual and free. Yeah, they're gone. Yeah.
Is this something a compiler, which doesn't know the physics of fast-forwardable models, would it just be like, oh, I can fuse these gates together?
Yes. Yeah.
The ZX compiler would do this like automatically.
Yeah. Will it really?
Yeah.
No, I didn't know that. Good.
Depending, of course, on what the specifics, but yes,
Yeah.
it's reasonable to think it would do that.
Yeah. Yeah, and basically anywhere within your circuit, if you find these things, it should be able to do that.
This is called peephole analysis, peephole optimization.
I see. Okay. I haven't seen this implemented yet.
Well, it's done classically, right? Because you're constructing something out of these 3
Yes.
blocks, right?
Yes.
You're not thinking about the whole structure.
Uh-huh.
And then you come back over again and look at the whole structure
Yeah.
and just collapsing these things.
Yeah, but I haven't seen this done automated yet.
No, not. Yeah. Well, there's some tools, maybe.
You want to see it?
Yeah. Okay. Good. The other thing that is nice about this is that the states that I'm going to prepare, the fermionic Gaussian states, they are also representable as one of these, which then means I can also absorb those in. So in the end, what I end up with is a relatively efficient state preparation, time evolution with only 1 ZZ per Trotter step, right? And a whole lot of the other things have been eaten away. And how much you gain gets better with the number of path size that you add. The rest of the structure is here because I want to compute a correlation function, right? Okay. Yeah.
So, great. Someone mentioned light cones. You haven't used that.
I did. It sits here. I ate some things that I'm not going to measure. But minimally so. It's not super. It's not as useful compared to the optimization you get per Trotter step.
So one of Google's papers, they said, we used alpha evolve 2 to make Trotter faster, and it found random light cone stuff, and it did things that we don't fully understand, but Trotter's better. Do you think that this is the most compressed version of this, or if you gave this to either smart grad student or AI, do you think it could smush more, or you feel that it's pretty smushed as much as you can get?
All right, I'll go on a limb and say this is the most smush you're going to get.
Good job.
Yeah. It is possible that you build some random things, and for a particular set of parameters, it will do better. But if you want this to work for all of your things, I don't think so. Okay. All right, good. I'm trying to be polite. So let's see what we get. That's what we get. Okay, so let me talk you through it. So this was run on an IBM quantum computer. We tried to run it on a different unnamed quantum computer, and the results were not usable. I don't know.
Who knows?
We'll have a poll afterwards to see which one you think you'll think it is. So these are the exact results. Noiseless Trotter is there. Just the results from Sherbrooke are these sort of dot things, these crosses, and then if you post-select and rescale a little bit based on the fact that you know that the initial one has to be 1, you get this sort of curve. Okay, it's not great, right? Like it's not what you would hope it would be even after all that work. So let me tell you in 2 minutes about the last thing. If you ask an experimentalist, which all of you are, right, what you should measure, the answer will always be you should measure a frequency. Because frequencies are much easier to tell apart from everything else than a number. Yes? You can do interference measurements, you can do all sorts of things. Fantastic. So the same is true here, right? These are not uncorrelated points. This is a spectrum. It's got analytic structure. It's got things that we know about it that we can make use of. So in particular, it turns out, and I'm enjoying this because I gave the same bit of talk 3 years ago, 2.5 years ago. It turns out that these things are positive semi-definite functions. It's a mathematical thing, which also means that if you arrange them as a matrix, right, where you put all the things this way, you put all the data this way, and its Hermitian conjugates on the left, this is a positive semi-definite matrix. Now, if you add noise to it, guess what? It's not positive semi-definite anymore. But what you can do is you can take your noisy data and project it onto the nearest positive semi-definite matrix. And in that way, take a bunch of your noise out. So this is some sine curve that I've polluted with some noise, and the green dots are what you get after taking the noise out. So let's try this on real data. This is real quantum computer data, not from what I showed you just now, but something else. This is the spectrum. Spectra are supposed to be positive. This is clearly not. All sorts of things wrong with it. So now you take this, you arrange it as a matrix, you ensure that it is the nearest positive semi-definite Toeplitz matrix, and what you get is this. Now I get peaks in the right place, sort of. I know where they're supposed to be, right? It looks a lot less noisy. It has some promise of being positive. That's good. The other thing is, now imagine that I had one more data point, fn plus 1. And now you can ask yourself, what number would this have to ensure that this matrix is still the most positive semi-definite you could have? And in this way, you would know one more data point. There's math that backs this up. I'm not just making this up. But you can go and extend it as long as your original data is good enough. So here's my original data. This is known. You can extend it. And in this case, it's easy because I only have 1 or 2 frequencies that live in this, right? So it's like a fancy fit, but better. So let's apply that to my quantum computer data. This is now, from here, we've gone to here. We've denoised and extended it. And this is the spectrum. Much cleaner, just by insisting on a very simple mathematical relation that this has to hold, that the noise does not. So we can do that for our DMFT Green's function. The denoising doesn't do too much, but the denoising and extending does. This is the raw hardware results. Just a Fourier transform. It's kind of garbage. If I denoise and extend it, this is what I get. And now it looks like I have something that I could kind of work with. All right, so we can use a lot of these things where we're not measuring numbers, but we're measuring correlation functions. OK. So that's my talk. I wanted to make one observation in the spirit of bridging the fault-tolerant quantum computing and asking for what's needed. And my observation is that I don't know very much about fault-tolerant quantum computing. And the thing that I need the most, right, is expertise from the people that do. Right? I come at this from like a domain scientist perspective. Right? I'm a condensed matter physicist. This is what I do. Right? And I do a bit of quantum computation. Right? But what I don't do is I don't do fault-tolerant quantum computing in the same way that a lot of people here do. And really what we need is sort of like, you know how we think about co-design for hardware? We need co-design for projects. And I think, you know, that was in some of your talk, right? And I think that is something that would help go a long way. OK, that's it. Thanks.